University. He is currently a senior professor at the Physical Research Laboratory at Ahmedabad. He has also been the head of the Theoretical Physics Division at Physical Research Laboratory. Professor Kota has made outstanding contributions in the area of theoretical nuclear physics. I will name some of these areas. Developing 1+2 body embedded random matrix ensembles with group symmetries for many body chaos in nuclei with particular emphasis on deriving analytical results. From Madras University and PhD in 1977 from Bombay University. Dr. Kailas is presently a distinguished scientist and director, physics group at ARC Mumbai, and also a senior professor of Homi Bhabha International Institute. Dr. Kailas has made outstanding contributions in the area of nuclear reactions. The highlights of his work are too many to mention here. I will just name some of them. First, systematic measurement of proton reaction cross sections for medium weight nuclei, development of the proton nucleus mean field, etc.
To thank the organizers, Dr. Chitkara, the Chancellor of this university, who was my ex-colleague at Punjab University. He just reminded me, but I knew it well. Perhaps he did not know that I come from Punjab University. And the registrar of this university, Dr. Grewal. On top of it, I thank on behalf of all five of us, the organizing committee, in particular my Guru Bhai Ashok Jain, we both were brought up by the same teacher, and my one of the youngest student, Dr. Sushil Kumar. I hope I can call him sometime, Professor Sushil. I'm really proud of him. I feel proud that I have some students of that kind who represent me. Perhaps there are about 25 of them. Let me say an anecdote here. It's not that always we get appreciation.
Gate overfolding model where you will calculate the cluster radioactivity or proton radioactivity. And for this thing, generally people take it is a M3OA interaction or DD-M3OA interaction. And this interaction, which consists of it, means a central part, a spin orbit part, and a tensor. And again, the central part is divided into the radial part, spin part, isospin part, and their interaction. But actually, if you see, the NN interaction should come from QCD. But it is very difficult to do this one, and yet we are waiting to get a potential from QCD level. And so what we do here, we take the next one. The next means not QCD, but before this one, which is effective Lagrangian, you can say. And then we take this RMF factor. And everybody knows, most of the people know that this is a very known Lagrangian. And this is applied for many of the cases, like a finite nuclei, nuclear metal, reaction, everything you can apply. Even it gives very good account for super heavy, also neutron star and equation. So we have taken this one, this Lagrangian, and we evaluate the NN potential, how it looks like. Instead of taking this M3OA, whether we can generate a potential similar to similar in the form of M3OA interaction. So once we know this Q value we get from experimentally or any theoretical model we can get this one. We know B and we know mu, and this is simple formula, and we can calculate this. So we get, and this is our result. This is with R3OA. R3OA means what I told already, it is from RMF, and M3OA means what we use basically, taking from the literature, and this we get almost comparable. So it is, we calculate this one, and here we add the Coulomb part and the scientific, because though the decay process can be treated as a simple quantum tunneling event, so a potential construct the proton nuclear potential in the single position with the point-like approximation of the proton and apply it to calculate the decay probability of the proton. The total interaction potential is the sum of the nuclear potential, Coulomb potential, and the centrifugal potential. So we get this potential like this, whether this region, and this is a typical example for this region. And this is our sum of the calculation. So if we take these are experimental value, this is with MCOA, and this is with linear RCOA, and this is with non-linear RCOA. And there are also some other experimental value available. If you compare this, our results is not very bad also. So what you can do, okay, you may need some improvement, but the similar type of things what you get from MCOA, you can generate from RCOA and apply to proton radioactivity as well as cluster radioactivity. And also you can apply to many other other. So this is also okay. So when we compare this is the experimental value, and this plot we did as a function of L in centrifugal. It matches with experimental value. So this model is okay. In summary, it is known that the question is that one thing, why we have put non-linearity. Non-linearity gives a complete model for RF. If you confine to only linearity, it gives large compressibility. That's why non-linearity is needed. And so it is known that the success of the non-linear model in reproducing the experimental results for finite wavelength is excellent. The nuclear compressibility it comes around 210, whereas for linear version it gives that. And the total interaction also show the similar behavior for both the cases, the active wave plus extent, being less attractive by above 1 MeV but with the barrier higher by compared to the active wave. As a consequence of the above result for proton radioactivity, the reduced E0 empirically are also affected. However, interestingly, in figure, we find that the values of this one are closer to the well-accepted and normalized formula of London scale, whereas the same for B0 are within 2-3 order of magnitude. Evidently, the effect of NN interaction obtained from the RMF Lagrangian, taking into consideration only the linear terms of the sigma, omega, and rho. While we study the phenomenon of proton emission of nuclei in the proton-rich region, it may be pointed out that the barrier height is a bit lower for the RCOA cases, and hence so are the penetration probability and the half-life of the proton. We have extended the application of the RCOA NN interaction model of exotic cluster decay to deal with the proton emission by including an angular momentum. The result presented for proton decay so that there are a number of proton decay cases that can be observed with measurable half-life. However, such calculated results can be treated as a useful information to predict the proton decay half-life as well as the observed in the proton decay. So, from all this study, we conclude that the improvement of the RCOA interaction or use of the most successful nonlinear RMF or ERMF Lagrangian is one. This work could be considered as the motivation for other similar models to generate the NN. And this R3 wave potential may be substitution of M3 wave in different cases. These are collaborators for this.
Yeah, it will be nice to first test in these cases of elastic scattering. Of course, imaginary you have to find, but real potential at least one can see whether they are similar or what.
cluster radioactivity and photon.
Hello?
It is not highly applied to us. This is recent.
Not direct penetration, it is stepwise. But you have shown it as direct penetration. I think it will lead to a error in your calculation.
Yeah, possible, because this is just a formula we use. Possible that it needs more improvement. But as a first step, wherever you want to apply M3 way, you can use here, no problem. Our main motivation that you can generate M3 way from a microscopic like that. Of course, you can apply it in real.
I have one comment actually. Can you go back to your previous slide where you show this probability or basalt frequency, what you calculate?
Morning is something about my research studying N equals Z nuclei and some of the very interesting physics that appears along the line of N equals Z. And in the interest of time, I'm not going to speak about this whole region, but just focus particularly on some of the research around mass 70. So here is the line of N equals Z. As was said this morning, at the bottom, these are stable nuclei. But as you go to heavier and heavier masses towards TIN 100, they rapidly become unstable nuclei and very, very difficult to study because the production cross-sections become very small. If we look at the odd N equals Z nuclei, this is making a vibration, a noise, is it? Feedback. Or is it this thing? The nucleus, the deuteron, you have the possibility of two different states that can be formed. One which is the isospin 0 spin 1 state, and one which is the spin 0 isospin 1 state. And you can have these two possibilities. Of course, the ground state of the deuteron is this favoured configuration. But when we go to heavier and heavier nuclei, the T equals 1 state wins. Beyond mass 50 or so, all the ground states are T equals 1. And the reason for this trend is not fully understood. Same orbitals is that you can have a strong role for neutron-proton pairing. Of course, regular pairing is important in nuclei, this residual interaction that brings down the ground state of the spin 0 plus state in even nuclei. But once we look at NP pairing, we have two different permutations that can play a role. However, if those two pairing modes were similar, and we looked at an odd N equals Z nucleus, then there's an explicit prediction by Chaseman on what you should see, and that is that you should see two states which are nearly degenerate, a odd spin state with T equals 0 and an even spin 0 state with T equals 1 that should be parallel, and then a large gap before you see other states. One of the complications, or one of the things that makes this physics very interesting along the N equals Z line around mass 70 or 80 is the very rapid change in nucleus shape, because we're in between the closed shells of nickel 56 and tin 100, and these are very old macroscopic predictions that you have not only oblate shapes like selenium 68, which is an oblate deformed nucleus, you have very prolate shapes up here like zirconium 80, one of the most prolate nuclei which you find. And many of these nuclei have a competition between two close-lying shape minima. And so it's a remarkable feature of the nucleus that you add a very small amount of energy to it, yet you completely change the nucleus shape. And this shows an example of an energy surface for Krypton 72, which is one of the best examples of this shape coexistence, with a prolate and oblate shape minima seen here. Now, one of the features of studying these nuclei is that they're also important for other areas of physics, and I always try and emphasize this for students, that it's not just nuclear structure here that's interesting, it's also applications to fundamental physics and nuclear astrophysics. Now, this is a huge topic in itself, but it should just briefly be mentioned that studying the beta decay of these odd n equals z nuclei, the Fermi superloud decay, allows you to test the CVC hypothesis and try and obtain a value for this VUD matrix element for the CKM matrix that relates to different quark eigenstates. And actually making measurements on these odd n equals z nuclei poses some of the strongest tests on this business which can be done, and they are done with nuclear physics and not from particle physics. The second area which I'll briefly mention is the area of nuclear astrophysics. And the scenario where this is relevant is that of an X-ray burst, which is a close-line binary system of a neutron star and a normal star, and material is infalling from the star onto the neutron star, leading to periodic flare-ups, which are called X-ray bursts. And in that X-ray burst, you have a very accelerated nuclear synthesis taking place along the RP process pathway, which lies along the pathway of very proton-rich nuclei, or n equals z nuclei, shown here. However, one of the issues is that many of the nuclei which would be in the chain are proton unbound. Here, for example, rubidium-73. And so that leads to the nucleus below, like krypton-72, being a potential waiting point in this reaction cycle. And these X-ray bursts typically have a duration of the order of tens of seconds, and so because some of these nuclei that are waiting points have half-lives of the order of tens of seconds, they can effectively be the endpoint or a stumbling block in this